Alrighty, good morning everybody and welcome to the wolfSSL live webinar on wolfBoot presented by wolfSSL Senior Engineer Daniele Lacamera. My name is Kajal Sipkota and I will be moderating this webinar. All attendees will be in listen-only mode. If you have questions, please feel free to use the Q&A box or raise your hand to be unmuted if you would like to ask the questions live, as we'll hold a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. I invite you to follow us on Twitter at wolfSSL, as well as all of our other socials. Also, please feel free to email us at facts@wolfSSL.com if you have any additional questions. And now, before we begin, I'd like to give a brief company overview. wolfSSL was founded in 2004 by Todd Auska and Larry Stefanik when they realized there wasn't an open source dual licensed embedded SSL library available. OpenSSL existed at the time, but there was a demand for an alternative that was easily portable, smaller, faster, available under a clear commercial license, was equipped with a clean and modern API, and offered commercial-style developer support. wolfSSL was born into this market need with an OpenSSL compatibility layer. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of almost 40 dedicated employees in 2020, most of which are engineers. This process, of course, is supported by a strong partner network that we're very proud of. Since the beginning, our engineering team has developed several embedded security products, including the Wolf Crypt with DO178 support, FIPS certification, as well as a FIPS ready offering, MQTT up to the version 5 specification, SSH version 2, TPM 2.2, a secure bootloader also known as wolfBoot, as well as Java wrappers and JSSC support and commercial support for curl. All of these offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. And now I'd like to turn things over to Daniele to talk about wolfBoot.
Thank you. Thanks everyone for joining this webinar today. And let's start with a brief introduction on secure boot and firmware updates. Let's talk about IoT, security in IoT. And as is tradition, we started a presentation about IoT with some numbers, about 30 billion IoT connected devices in 2020. This shows how massively embedded system devices nowadays rely on internet connectivity and how much security is important. Because we also know that internet connectivity poses some threats to the security of the connected devices, and of course there is this running joke about the S being the security, standing for security in the IoT acronym, and we hope that this is not true anymore, because we are able to identify security threats specifically in the IoT environment, and we should address security problem the same way as in traditional IT environment, also in IoT. So let's talk about vulnerability management. This is a very important aspect in all connected systems. It's about using the best technology up to the latest standards, as ETF recommends. TLS 1.3 is the standard today for the best secure connected socket connectivity, and delivers superior privacy, security, and performance. And of course, being able to deliver a product with up to standard security doesn't mean that it's not a static process. So once the product is delivered, everything must be kept up to date. So every time you discover new vulnerability or one of the components in your system is affected by known vulnerability, being the embedded software architecture often being based on a flat model, especially on microcontrollers, a single vulnerability of one component usually compromises the entire system. And even TLS, which is the highest grade of standards in security for data in motion nowadays, may be compromised, as it happened in the past with the previous versions that had been patched. Sometimes it's not just a matter of implementation, and it's there are vulnerabilities that are discovered in the design of the protocols as well. So this means that the secure updates and the remote updates are a security requirement for IoT connected devices. And so let's explore a little bit what kind of treat we can expect from the IoT in general. And those are the problems that we're going to address with the secure boot mechanism. So running unauthorized firmware on the target. So malicious third party could try to inject forged firmware to run on your device, or an attacker could try to physically access the debugging interface of your deployed project or system, and could be able to extract data at rest from the storage memory. There are several types of attacks that are more actively targeting a running device, so arbitrary code execution, even from a remote location. This is usually due to poor memory management, memory safety measures in place, and of course there is IP protection convention that can go as deep as very expensive attacks as scanning electron microscope attacks. So, what about firmware updates? What does is there a standard already we can follow to implement this kind of features in our microcontrollers? Well, there is a draft of a standard which has been developed by the IETF group named SUT, which is short for Software Update for the Internet of Things. And this draft is very specific on the countermeasures to take, especially against counterfeiting firmware updates, but also giving some guidelines on the security aspect, on the safety aspects of the bootloader software that has to be installed on the device. And especially the bootloader must be small in its implementation, particularly the standard, the draft focuses on small parsers, because parsers are often a source of safety bugs that can translate, of course, in such a critical component as a bootloader in compromising the entire system. It needs to have high reliability, because a single bug in a device that can't be physically accessed means that it's not possible to install or just run the current firmware if there is a critical bug in the bootloader, and so on. But especially it mandates the use of state-of-the-art security mechanisms, and this means that has to be based on asymmetric cryptography to verify the authenticity of the firmware, and of course hash algorithms to verify the integrity of the firmware itself. So, what's the approach mostly taken in the market historically? Do-it-yourself secure bootloader. what are the hidden costs of this? It is a massive project, not just because of the coding part, but it's all the testing related to the bootloader must be predictable, must have a predictable behavior in all the corner cases. Whenever an update fails, and it has it needs a key management mechanism in place that integrates also with your host systems when you're creating the keys or when you're managing the signatures for the firmware updates before putting it in the life cycle of the product. So we have seen this a lot in the past, which is one of the reasons that pushed us to write a more generic solution for secure boot and secure firmware updates that would fit in many different and heterogeneous projects, from microcontrollers up to microprocessors running Linux, for instance. So this means that we are dedicating a full-time engineers to work on this, and that's probably an effort that your embedded project should not face. In the same way that you shouldn't write your own TLS library, but you should use wolfSSL. You shouldn't write your own TCP/IP stack just because you need internet connectivity, but you're probably going to refer to an existing implementation. Or same thing for a real-time operating system. So we also believe that this is true also for a bootloader, because it's a critical component. It requires a lot of testing and to cover all the corner cases, and it relies on perfect synchronization of all the components, also during the end-of-line testing, production, and deployment. So our goal was since the beginning to prepare a universal secure bootloader. So at the top of our requirement list was for sure the portability across all the 32-bit microcontrollers, to be as much as hardware independent as possible. And the hashing algorithms, as well as public key firmware authentication, was never a problem, because that's already well-established technology present in wolfScript, which is the crypto engine that powers the entire wolfSSL library, and all the secure connectivity and the secure technology and encryption in the wolfSSL environment. We focus, of course, on small footprints, because our target is to run on the smallest microcontroller on the market, which means normally in the range of Cortex M0s with very, very little resources in terms of memory and storage space. We focus a lot on memory safety, we will see, because that we believe it's an attack surface, not taking into account all the boundaries that can be accidentally crossed in memory while coding on those devices. And we wanted to provide a reliable firmware update mechanism, which is, as mandated by SWIFT, completely independent from the update transport mechanism, and has a fallback to a previous version in case something goes wrong. When updating to version 6, you can always roll back to the previous version 5 that has been backed up by the bootloader into a temporary partition. So that's how wolfBoot was born. wolfBoot is nowadays a very popular open source secure bootloader, especially in the microcontroller area, but not only. It's been designed for the IoT since the beginning, so we follow the SWIFT requirements, even a few versions of the draft back from now. and it runs on most 32-bit microcontrollers. We support all ARM, Cortex-M, RISC-V, RD32. We do also support 64-bit systems like RMD8 with Trustzone, so we can run on Cortex-A. And of course, that most of the time requires a more complex setup to go through the entire trust chain. But we are able to integrate the bootloader with different at a different stage of the boot process. And it is OS agnostic. It can be integrated basically with any operating system. The only requirement is to move the beginning of the endpoint for the executable. It can be, of course, RTOS or a bare metal application. So the linker script of the final application must be aware that there is a bootloader at the beginning of the flash partition, and it has to be linked at that physical address where no virtual memory is present, so for instance in microcontrollers. And but on the other hand, when running on 64-bit systems, we do also provide support for kernel and rootfs updates, device tree, etc. We wanted since the beginning to provide the support for perfect chain of trust integration in the easiest, let's say, the simplest configuration. wolfBoot works as a standalone bootloader, and it comes with its own key generation and signing tools. And in the simplest configuration, you own your own keys, and you're able to sign the final image and verify it using a public key embedded in a bootloader. And but in more complex cases, like for instance when there is a hardware module that's in charge of signing the updates, or a third-party provisioning service, then our key tools can split the operation and allow for a third party to interact with the trust chain in order to have final firmware that's trusted by multiple parties at the same time. How does it work? It uses this public key authentication mechanism. It can be DSA, so RSA based, or ECDSA, so with elliptic curves, which is provided by wolfScript to verify the signature that's being attached to the bundle of the firmware image that's being transferred. And it supports secure elements on board of the target to offload, for instance, the calculation of the verification of the public key mechanism, or other operations that are done, for instance, checking the integrity, calculating the hash through a SHA algorithm. Those operations can be offloaded to an external module, and such as secure elements or a crypto hardware accelerator that are present in many microcontrollers today, and also supported widely by wolfScript that has a dedicated driver section for interacting with those devices. It supports TPM 2.0 devices through the wolfTPM library, which is also part of wolfSSL offering, and it's basically a component that allows to integrate TPM devices with the entire wolfSSL ecosystem. The parser, as we said previously, is very small, and it's about 30 lines of C code, and that's all it takes to parse the manifest header at the beginning of the image. And so safety in mind, that the parser is very small, there is no dynamic memory allocation allowed in the code, so no malloc, no free. Every piece of memory that's used during the bootloader lifetime is pre-allocated at compile time, so that there are no surprises if you're exceeding the usage of your heap. due to a customization of the bootloader or because of running on a specific hardware with very, very restricted resources. And recently added support for such a 20 encrypted external partitions. So as we would see, the bootloader supports storing the updates on an external partition, such as SPI flash or any non-volatile memory that's not marked for execution at runtime. It can still be used to store temporarily the update that has been received. And this update can be now encrypted at the source. So when you're signing, you can also encrypt the bundle that contains the firmware and its signature. And when it's sent to the device then can decrypt before authenticating. And but this is only available, and it makes sense, as we would see, if the update is stored to an external partition, such as an SPI or a remote partition through a UART link that we also support. An extra thing that we support that's not specifically mandated by the draft. The draft is a bootloader self-update. So wolfBoot is capable of receiving an handling self-update, so it's capable of updating itself. If it receives a bundle that is correctly signed that contains an update for the bootloader, it is capable of processing it by jumping into RAM and writing the new update into the partition dedicated to the bootloader itself at the very beginning of the flash. We, as I already said, we provide key management tools which are distributed together with the bootloader. We provide and maintain two flavors. The C version that's portable to all operating systems. It depends on wolfSSL, and the Python, which is a set of scripts that with the exact same syntax as the C tools, that depend on the wolfscript PY package on the Python repository. And both these tools are easy to integrate with third-party key provisioning. As I was saying, the key signing operation can be split in half to allow third-party to join the process of creating an authenticated firmware. And as everything else we distribute and we work on at wolfSSL, we work full time on new features, bug fixes, but you can check this by yourself because all our development is publicly available on GitHub, and you can see how often we release and how quick we respond to new feature requests and bug reports. And we do, of course, offer ad hoc support packages up to 24/7 if you're using wolfBoot in any of your products. As we said, portability, so the hardware abstraction layer allows for a very little amount of platform-specific code, and the support for external flash, and as I said just now, all the code is available under GPLv2 and Bootloader. So if we have a look at the architecture of your embedded system that supports secure boot, so on the left-hand side you see the bootloader. The blue parts are those that are already part of the wolfBoot package itself. The green square contains a public key trust anchor, which can be compiled in, like in this case, where public key is just compiled in buffer wolfBoot, or can be, of course, stored on an external secure element, such as a TPM device or a hardware secure storage or one-time programmable memory. And the orange part, this is the flash driver. This is a small amount of code that's target specific. We do provide already that flash drivers for a large number of platforms, but it's on the other hand very easy to port it to a new platform we don't support. again, it's all about a few tens of lines of code, and it's normally either coded directly on the microcontroller register or to port package. But both possibilities, both options are possible. On the right-hand side, you have your own application running with all its components. Probably you will have CPD stack, TLS, support to wolfSSL. You already have a wolfScript module, and we just can add a little library called libwolfBoot, which just consists of two function calls most of the time. One is to initiate the update, and the other one is to confirm that the update that just happened has been successful, because the application is alive again, and can confirm this to the bootloader by writing a flag in a specific location in Flash. And that's done automatically by this library that can be integrated in the application. And of course, that library can also use either the Flash driver already present in your system, or can be integrated using the same other abstraction layer that's used by the bootloader. In that case, that piece of code is shared between the application and the bootloader itself. How does it work with key management? Very quickly, the key pair is generated once, so we generate a key pair of a public and private key. The private key stays on the server or on the developer's machine, and it's used to sign the bundle that contains the software update. While the public key is stored somewhere in the target. As we said, this can be compiled in a buffer, and the bootloader itself, the public key doesn't have to be secret. The only thing that we should ensure is that it's never modified. Like the device is, for instance, physically reachable, it should have a mechanism to protect against writing the flash, like a write protection mechanism on the flash. And the sign tool, whenever you sign a new bundle, it attaches a header, that's a manifest header, to the firmware image itself. And this header is of a fixed size, and it depends on the algorithm that we're using, which require the header to contain the signature for the firmware itself, and the digest for the hash verification. And so wolfBoot in the end relies on the trust anchor. The trust anchor can be either, as I said, in the easiest case, just compiled in the bootloader and don't allow anyone to modify it, probably with a hardware protection against writing on the flash. This is how a trust anchor is described by the standard, again, IETF, RFC 6024. Basically, in our case, in the simple case, it's just a storage that is present in the device, and it contains our public key, and we have to trust that nobody is capable of modifying that public key in order to be able to trust the firmware itself afterwards. So this is a requirement that must be achieved in your project regarding the trust anchor storage. It must resist modification against unauthorized insertion, deletion, and modification, and which is also enforced, by the way, by the syntax. The flash readout protection, in most cases, when it's provided by your hardware manufacturer, it's sufficiently secure, but does not cover you from all hardware attacks. We talked about very expensive scanning mechanisms that can look at the bits inside of your PCAP microcontroller while the chip is running the code. Sorry. So the best way for bulletproof, let's say, trust anchor storage for your secure storage for the secure boot should be a trust anchor that's implemented via hardware secure element. And of course, this can also be done, and some manufacturers do this. The trust anchor can be written in the factory for you with a specific anchor that's specific to that single device, and then they will provide you with the private, the secret material associated to that anchor for that device. So just to recap on this key management mechanism, imagine you're generating the key the first time, and of course it's a key pair. The private key is stored in the server. The public key is used at compile time to link together the wolfBoot sources to have compiled wolfBoot that self-contains the public key in a buffer. Then you have the firmware image, the version number, and the private key on the server side. You combine these three with our sign tool on the server, and of course, the private key should never leave your secure server location where this operation is done, in order for the authenticity of the firmware that's been signed to be guaranteed. And in the end, you obtain as an output authenticated firmware that wolfBoot will be able to authenticate thanks to the public key. So this is very simple from the cryptographic point of view. From the point of view of the update management, there are two possible strategies that we both support. There's also a little bit more than this, but let's say this is the two biggest categories of strategies for implementing an update management. So there's an AD approach. So the two partitions are in non-volatile memory, but they share the same level. So there is no primary and secondary. You just select at boot time which one you want to start from. But of course, this requires position-independent firmware, and it requires that your device supports jumping to two different locations. Or maybe if your device has a physical memory mapping, like in most microcontrollers, this requires you to associate, for instance, the entry points to the firmware number, to the version number, so that even version numbers will always boot from partition B and odd from partition A. So it's not really handy, it's not very comfortable to manage from the production point of view. The boot update approach is the other way around. So we do have a primary partition, and that's where our primary firmware is always going to be. And we receive updates to an update partition, and that's acting as a secondary partition. And every time we want to install an update, just swap the contents of the two. So the AB approach is nice, very fast, but it's not recommended for microcontrollers, while we can use it without any problems, for instance, on 64-bit platforms running Linux. Because, of course, it introduces these kind of constraints, and also it has the other downside of not allowing updates to be stored on memories that are not executable in place in the microcontroller world. So if you want to use an SPI flash device to store your updates, this is not possible because you couldn't be jumping on partition B. So in the most common case for microcontrollers, we go for the boot and update. So this means that it translates into this kind of partition. There is one small partition in the beginning that contains wolfBoot. Then there is the boot partition, as we said. The firmware will always start from there. And then there is the update partition that the application will use to store the downloaded update. And then little swap partition, which is normally the size of one page in a flash, so between 500 bytes and 2K, for in some cases even 4, which is used to keep just one sector of swap when doing the swap operation. So, and update the swap partitions can be mapped on external non-volatile memories such as SPI flash, and to also unlock this would also unlock the possibility of encrypting the content and storing this update encrypted. For what concerns the rollback mechanism, that's how it works. So imagine you're running on the situation on the top half, so you have firmware version 1, and you receive a firmware version 2 in the update partition, that's one marked in green. And then wolfBoot at the next reboot will swap the two images using the little swap partition at the end, the yellow one. So if everything goes well, then the firmware number 2 will now run normally on your device. But if something goes wrong and your watchdog takes another reboot, then the bootloader will find out that the firmware version 2 has never been confirmed. So it will roll back to the situation and stop us again. Just for the integration with the operating system, the file application in general, bare metal or RTOS, has to move its entry point to take into account the presence of wolfBoot itself and the manifest header. In this example, we are using a few kilobytes of the flash at the beginning to store wolfBoot, and just 256 bytes of header. Which is the case with all the elliptic curves, and so the firmware entry point will move from 0, that was the original linker script on top, to 6100, which is the new address where the firmware image actually starts. Please notice that the header is inserted by the set signing tool, so it will be automatically pre-valid to your firmware during signature. So the manifest header contains all the information, the metadata about the firmware itself, and this is basically the type of structure that's being parsed by the bootloader when it's evaluating the update, or even when it's checking that the current running firmware is authenticated and can run. So in a real life scenario, you have this device, you put wolfBoot, and then you flash your factory firmware, probably version number 1. As we said, you need private key, and you can do this in a factory scenario, let's say, so still using the JTAG, but from that point on, your JTAG doesn't you don't need your JTAG anymore, because everything will be done using in-application programming. So whenever you start in the first time, you just have the wolfBoot and the current firmware. On normal condition, you just authenticate the firmware, and it will just run the application, which in turn can also receive an update through the internet, for instance, that has been signed and versioned correctly by the same server, or at least using the same private key, and then transmitted using any OTA mechanism and stored by the application in the firmware update partition. After the reboot, the bootloader will verify the update and then swap the two images in place, and then ensure that the firmware update becomes now the current firmware. And in the update partition, as you can see, there is a backup of the previous firmware. So if everything goes well, the update is confirmed, and then the old firmware is erased, and from this moment on, the system is again ready to receive the next update. If something goes wrong, the images are swapped again, and then the previous version is put back in place. It's the confirmation of a valid running firmware never came from the application itself. And then the system is again capable of booting over. To conclude this, just say this is our default logic flow. Everything that's done in the bootloader application is predictable from the flow point of view. This is our default application mechanism, and it's again something we can customize, or you can customize yourself to the use of your own product, and which basically applies the boot update partition mechanism by verifying if there is an update present that has been communicated to the API, and then the authenticity of it, and start the update mechanism in case, or in the normal flow, let's say, it just follows from reset to staging, just by verifying that the current firmware is still authentic and it still corresponds to the metadata that were attached to it. And talking about the swap operations, just one last note. On most platforms, those are fail-safe. So power can be interrupted. The microcontroller can be even reset during the update procedure. And due to the structure with the swap partition, there always exists 2 copies of the same payload content in at least 2 partitions. So the write operation that's been interrupted is identified as next reboot, and the swap operation is resumed before any other operation. So basically, the state machine in the previous slide is resumed exactly from the point where it left. This ensures basically that we are safe against the device breaking if power failure occurs or it runs out of battery at the worst possible time, and just receive an update and installing it, because that's what's going to happen. And this feature relies on a feature that's available on most microcontroller flash controllers, which is the possibility to write 0 to the flash without reading the entire page. We do have a workaround for this, but it just reduces the possibility of breaking without completely excluding it, unless this feature is available on the board. So that concludes my presentation for what concerns wolfBoot. I guess we still have time for questions, so I give the stage back to Carlo. Thank you.